Hello, everyone. My name is Krista Milbury, and on behalf of the Foundation for Conservation of Atlantic Salmon, I would like to welcome you to today's webinar. Today's webinar will be presented in English. However, we have AI translation available. If you wish to use the translation, please navigate to the chat where you will find instructions on how to connect. For today's webinar, we are very pleased to be hosting Dr. Travis Van Leeuwen. Travis has a PhD in ecology and evolutionary biology and is currently a research scientist at Fisheries and Oceans Canada, located in St. John's, Newfoundland. Before arriving at DFO, Travis's research focused on the effects of individual variation in metabolism on life history patterns and adaptive trade-offs across species. During his master's at the University of British Columbia, he studied links among life history strategies, physiology, and growth in juvenile salmon. During his PhD at the University of Glasgow, he studied the physiological, morphological, behavioral, and developmental differences between offspring of brown trout from alternative life history in an attempt to better understand the causes and consequences of partial migration. Today, Travis will be speaking on catch and release of Atlantic salmon in a changing climate, considerations for anglers, scientists, and resource managers. After this afternoon's presentation, we will be opening the floor for questions and answers. Now, I will turn the webinar over to Travis.
Perfect. So good afternoon, everybody. Thank you for attending the webinar, and thank you to the Foundation for inviting me here today. So let's just get right into it. Title of the webinar today is Catch and Release of Atlantic Salmon in a Changing Climate, Considerations for Anglers, Scientists, and Resource Managers. So we're really going to cover three really applied science questions. And so those questions include, what is the relationship between the survival of Atlantic salmon and water temperature at the time of the catch and release event? Do acute water temperature changes before and after the catch and release event influence survival of Atlantic salmon? And how can various water temperature related fishery closures affect outcomes for the salmon and angler? And so throughout this presentation and throughout the data, I'm going to assume best practices. I don't think you need me to tell you about, air exposing fish or beaching fish or handling them roughly, has detrimental effects on survival. And so I'll assume, everybody's doing their part and using best practices. Now, as many of you likely experienced, warm water temperatures are having, likely consequences on salmon, and also having consequences on angling opportunity. And so here's a paper that we published last year related to some unprecedented warm water events that occurred in Labrador in July of 2023. And so up here in panel B, you can see we got water temperature on the y-axis, and on the x-axis, we have date. We had water temperature data for 7 rivers, and that time series went from 1994 to 2023. And you can see this dark sort of black line here. That's the average from 1994 to 2022 for those rivers in Labrador. And then you can see that blue line is the water temperature, the daily average water temperature for 2023. And you can see that for most of July, a very big warm water event occurred. And so in 2023, the monthly and daily average and the percentage of hours in July in which water temperatures were above 20 degrees Celsius were the highest recorded in the time series. And so and then in panel C here, it's just showing that likely coincided with returns of Atlantic salmon. And so given some of our counting fence data, it suggests that 67% of Atlantic salmon were present during this period when water temperatures exceeded 25 Celsius. And so 25 Celsius is that number that you hear a lot, that water temperature you hear a lot, that is believed to be the incipient lethal level for Atlantic salmon. And then, so, likely consequences on salmon, but also likely consequences on anglers. And so in panel D here, we just have a number of rivers here. And on the x-axis, again, we have date. And so there are morning angling only restrictions on 16 rivers and complete angling closures on 4 rivers. This was the greatest number of angling restrictions ever recorded for Labrador, and that data series goes back to 1975. And to give you a little bit of context on how unprecedented this actually was, is prior to this warm water event that occurred in July of 2023, Shinny's River was the only Labrador river ever closed to angling. And so catch and release research in DFO is really nothing new. It's been a topic around DFO for a long time. Here's just some examples in black. In no form is it exhaustive, but really over the last kind of 4 or 5 years, we've been adding to this literature, our group, and these are some of the papers here in red that I'll touch on during this webinar. But feel free to look those up. They're all published. They're all available in the online. And so let's get into our first question. So what is the relationship between survival of Atlantic salmon and water temperature at the time of the catch and release event? And to answer this question, I'll approach it from 2 angles. So the first approach will be a data synthesis approach, and this is just using available data at the time. And then the approach 2 is a field study on catch and release that the province of Newfoundland and Labrador did with in-kind support from DFO. And so let's talk about the approach 1. So this is a data synthesis, meta-analysis type approach, really a desktop approach to understanding the relationship between water temperature and catch and release survival. And it built on existing work by Dempson and Havin and Lennox. And it basically just pulled data from published and unpublished studies investigating the effect of catch and release on mortality of Atlantic salmon. We then applied a general linear mixed effects model with a binomial distribution. So number of individuals that died versus number of individuals that survived for a given study. Temperature was modeled as a polynomial term to allow curvature in that relationship between the probability of mortality and water temperature and provide a model of best fit. We also included reference in there. This is the literature source as a random effect control for multiple estimates of mortality at various water temperatures from a single study. And so again, this paper was published back in 2020, and this was really our group's first sort of dab into this question. And so here you see those studies that we pulled from. There were a number of studies at the time, and it's worth including that, a lot of these studies use different techniques, lab-based, field-based, held fish in cages versus, using different forms of telemetry, also different life stages of salmon. We had, multi-sea winter, 1C winter, kelp. And so this is really a way of just pulling all that information together and seeing what this relationship was. So if you just look purely at that data, catch and release mortality for anadromous Atlantic salmon across studies ranged from 0 to 80% for mean water temperature between 1.2 and 23 degrees Celsius. But what's important is 66% of published data having mortalities of less than 10%. And if you include one in each, 75% of published data having mortalities less than 10%. And we'll talk a little bit more about, that range and how we dealt with some of those age ranges, those ranges of mortality. And so part of that data, that meta-analysis, data synthesis type approach is we also recorded on whether those studies included a control. And so basically a control is often needed to basically, determine, what are the effects of everything but the catch and release event. And so you can see from the published literature, it was very, very low. And so basically in terms of control, mortality associated with the various procedure controls in the published data is very low, 0 to 0.06, so i.e. much less than 1%. So basically we did no subtractions to our data because the controls from those studies suggested very little mortality in those individuals. And so this is what the model essentially looks like. So on the y-axis here, we have probability of mortality. On the x-axis, we have mean water temperature. These two figures are exactly the same, A and B, but what we're just trying to show here is that, one is the dots are partitioned by life history stage. So red is just showing 1C winter, kelp, multi-sea winter, 1C winter. Obviously different regions, we'll have different proportions of different life history types. And then we just did the same figure over here, just showing, really the different angling conditions that were used. So whether it was a laboratory-based study that used a chase protocol to simulate catch and release, fly fishing only, had a multiple of fly fishing and lure fishing, and also lure fishing. And so here's that relationship that we put through those lines from those various studies. And you can see that very clearly that there's a significant relationship between the probability of mortality and mean water temperature. And I think what's important here to tell people is that, that relationship is not linear. And you can see that, at these very low temperatures, catch and release mortality is very, very low. But when you start moving into kind of these warmer water temperatures, whether it be, 18, 19, 20 degrees, that effect becomes multiplicative. And so it's not just some sort of linear increase. It means that as you increase that water temperature, you get to a certain point that the mortality starts increasing quite rapidly. And so as part of this, I did mention it earlier, there was some sort of discrepancies within some of the studies when we were presenting this stuff during various CSAS meetings here with DFO. And one of those was a study by Anderson et al. 1998, which used heart rate tags to not necessarily to look at the survival, but it was more to look at the physiology of a catch and release event at various water temperatures. And so they had very little mortality or zero mortality at 8 and 16 degrees, but then they had this quite sharp increase of mortality at 20 degrees. And so, but again, at 20 degrees, it was 4 of 5 individuals died at that temperature. And so instead of just, removing that study completely, we did a bit of a sensitivity analysis. So we looked at the model with that data included and without. And then also, there's a few other studies here with asterisks. These are primarily from Norway, and these were Norwegian studies. And basically, they had different regulations around the release of a critically injured fish. And so, for those studies, critically injured fish, as part of that, were not included in those survival or in those mortality estimates. And so, based on Eastern Canada, we don't have those same regulations. So those fish would be expected to be released. And so we added those individuals where appropriate into the analysis. But again, we did that sensitivity analysis. So with that Anderson and al. Paper included, and then with those critically wounded fish included or excluded. And so what you see, in that sensitivity analysis, it doesn't really change the ball game too much here. And so at 15 degrees, whether you included them or not, you're looking anywhere from about 4% to 7% mortality. It starts ramping up 18%, anywhere from 6 to 13, 7 to 16, and 8 to 20. And that's sort of on that lower 95% confidence interval to the mean. And so part of the consensus of one of the CSAS meetings that we had here is that given that Newfoundland and Labrador uses single barbless hooks and fly fishing only, we would estimate that mortality associated with catch and release in Newfoundland, now this might be applicable other places elsewhere, is likely on the lower estimates reported here. And also we have to keep in mind that, fish in any one of these studies are likely subjected to greater procedures and handling than what is, maybe typical. And so, we were comfortable with saying that, of these estimates, lower 95% confidence intervals, we're likely falling in the lower to kind of mean average here. And so the second approach was a study that was funded by the province of NL with in-kind support from DFO. And so the study took place on Western Arm Brook in Newfoundland. And so if you're not familiar with Newfoundland, it's up here on the Great Northern Peninsula. The reason why that river was chosen is it has a history of data collection going back to the 1960s. It's had a counting fence on the system since 1971. So really good counts on smolt and adults returning. And it's been closed to angling since 1989. And this is important because, we're using a field-based area, acoustic telemetry, radio telemetry. And so we didn't have to worry about, issues with anglers, catching these treated fish or the fish used during part of the experiment. And so this was a paper that we published in 2002, way more detail in there than what I'm going to focus on now. So I'll briefly just touch on the methods. So this was a study conducted from 2018 to 2020, so field seasons in 2018, 19, and 20. It used a control group. So these are individuals that were dip netted from the counting fence trap, and there was 164 of those individuals. And then there was 119 individuals that were angled over about a 6 kilometer stretch of the river, basically from the counting fence up to about 6 kilometers. It used radio telemetry and a combination of internal and external tags, and that's what those tags look like here. So here's just an example of an external radio tag. The tag's here, so the battery would be down here, and then a streaming antenna off. And this is just an example of an internal tag. The tag goes in, and then you have a streaming antenna coming out of it as well. And so there's a couple of reasons for using two types of tags. One is for the internal tagging procedure. It's very quick. It uses one of these flow tags that you can attach a tag to, so no anesthetic. The fish is basically caught, netted, and then the tag inserted, and then that fish is released. The issue with external tags is that they can't be very large. And so without a large tag, the battery life is shorter. And so the external tags only lasted about 5 months. Now with an internal tag, you can get away with a little bit larger tag. And so that tag, the battery life's about 2 years. So basically, because we wanted to look at short-term and long-term survival, we used a combination of both tags. So mean water temperature for the entire study was 15.8 C, but angling events ranged from 5 degrees Celsius to 22 degrees Celsius. Mean size of fish for the study was about 54.4 centimeters and ranged from 45 to 74. And so what's important here to realize is that with the control group and experimental group is, really what we're evaluating here is the added effect of the catch and release event on survival. And we looked at long-term survival, so from 1 to 300 days. And so a little bit more about the method. So in order to know the positions of fish once released, there was 7 solar-powered telemetry stations used. So these are those telemetry stations here with a radio receiver. So as a fish swims upriver, those radio receivers, the transmitter from the tag can be picked up by the radio receiver. It provides a unique identifier code and a date, and obviously we know the position of those receivers. There was manual tracking done, so using the same setup but walking the river with it, and also 49 telemetry monitoring flights so that they were able to look at positions of fish, again, 1 to 300 days, and over the entire system. And so here's just a figure showing different aspects of the system for the control fish and experimental fish, and just some event locations. So this could be anything from the last known position after a battery failure, a mortality. This could be a kelp moving down and past the system. And what it basically is trying to show is that whether the fish was a control group or from the experimental group, they all used the entire length of the watershed. So there was individuals picked up at the bottom and also at the top of the watershed. You can see in the angled and in panel B here, the angling took place in designated areas. And that was anywhere from about 6 kilometers from the counting fence location. And obviously all the fish as part of the control were released from the counting fence. You can see the locations of those 7 radio telemetry receivers, again, spread out through the water course, and then the location of the counting fence. And so let's get into a bit of the results. So there's a couple of ways to look at this. There's a survival probability overall for these fish at a given water temperature. But really, in terms of understanding catch and release, it's really the difference between the control and the experimental that's the added effect of the catch and release event. And so one thing that I should note here is that during the study, there was marks and sores observed on some fish handled with cotton gloves. So very early on in the experiment, there was some cotton gloves used at the counting fence for the control fish, and it only occurred in year 1 for external control tags. But what was noticed soon after was these marks and sores appearing on those fish. Now, it's not as simple as just throwing that group away. So what we wanted to do was actually present the data with those cotton glove fish included and the data with the cotton glove fish excluded. And the reason why we're unable to really evaluate, the effect of the cotton glove is that, we don't know if all the fish that were handled this way resulted in marks and sores. But what we do know is that not all fish died that were handled in this way. So it's unclear whether it's just specifically the cotton glove or it's a combination of, too much pressure on the caudal peduncle plus the cotton glove. But it's worth noting that as we go through this, I'll talk about 2 control groups. And so in panel B, this is that data set 1. This is when the external controls from year 1 were excluded. So these are cotton glove excluded fish. And in panel B is with those cotton glove handled fish excluded. And so the control fish, those are again the ones that were captured the counting fence, tagged and released, are in red, and then those angled fish are in blue. And so really what we're looking at here is the difference between those angled fish and the control fish is the added effect of the catch and release event. And so what you see is there's a lot of overlap in the 95% confidence intervals here, whether the cotton glove fish were included or excluded. And so overall, there was no significant difference in long-term survival between Atlantic salmon that were angled, radio tagged, and released, and the control group. Now, again, this is at, over the entire study, average water temperature 15.8 Celsius. However, when we start looking at the effect of water temperature on this, we see a little bit different story. And so here's 3 panels, and with on the y-axis we have survival probability, on the x-axis we have water temperature at the time of capture. And again, we looked at this at 1 day post-release, 10 days post-release, and 30 days post-release. And so one of the things that, and so in the red dotted line here, these are those 2 controls that I talked about. So with cotton gloves included and excluded. And then the black line here is the survival probability at a given water temperature for the angled fish. And so you can see at 1 day, 10 days post-release, and 30 days post-release. Now, one thing to point out here is the difference between this black line and the red line. That's the added effect of the catch and release event. And so you can see that there's a significant difference between the angled fish and the control fish at 1 day post-release, but that the control fish and the angled fish, the survival probability converges at 10 days post-release and 30 days post-release. So meaning that the added effect of the catch and release event is relatively short-lived in this context and occurs somewhere between 1 and 10 days post-release. And so, when we're talking about catch and release and water temperature, these are the values that we're talking about here. And so let's, jump into what some of those values look like. So here's that survival probability. Again, the added effect of the catch and release event happens essentially between 1 and 10 days post-release. And so, you can see at 10 degrees Celsius, similar to what I showed you in the meta-analysis data synthesis approach, we have the 95% confidence intervals, the mean, and then the upper 95% confidence intervals. We then calculated a mean with a cotton glove included fish and a mean with a cotton glove fish excluded. And then the difference between that two is the survival probability. And so you can see it's essentially 100% at 10 degrees. But when we start moving up at 18 degrees, it tells a little bit different story. So we're talking about 92% survival in the catch and release group, 93% survival if the cotton glove handled fish are excluded. And then at 19, the added effect is about 11%, or survival is 89%, 91%, 85, and 87 at 20 degrees, and so on. And so just to sort of bring, my 2 approaches, or the 2 approaches together, this is just showing a figure with survival on the y-axis, water temperature at the time of the catch and release event on the x-axis. So the blue lines there is the study I just showed you. That's the field-based study at Western Arm Brook, the Keefe study. And then the green lines here are the meta-analysis or data synthesis approach that I showed you earlier. And you can see that there's a lot of consistency amongst the two approaches. And again, whether those different studies or what have you are included or not. And so if you just draw in at 18 degrees Celsius, you compare that at 20, you're talking fair bit of agreement amongst the different models. You're talking maybe 2 or 3%, either way of the different models. So a lot of agreement between what we're seeing in the literature and our data synthesis meta-analysis approach, and also what we're seeing in this Western Arm Brook study conducted by the province. So the second question that we're going to ask is, again, using the Western Arm Brook data, is do acute water temperature changes before and after the catch and release event influence survival of Atlantic salmon? And so this is a paper that we published in 2024. It was really just of interest. There was a lot of talk around whether cotton release salmon are able to recover better if they experience cooler waters after the catch and release event. And so here's just some data from across rivers in eastern Canada, primarily Newfoundland, Labrador, but also New Brunswick and Nova Scotia. And what on the y-axis here we have water temperature, on the x-axis we have the fishing season date. So fishing seasons differ a little bit depending on river, depending on region. But what should jump out at you is that water temperature changes obviously throughout the angling season. It also changes, almost daily, but also within a day. So there's considerable variation in water temperature within a day. And so primarily when you evaluate water temperature, we can look at morning water temperatures and then mean day temperatures. And so each one of these figures has a black line here, just showing that the daily average water temperature over the salmon over the season. And then the gray lines here are the average morning water temperatures. And you can see that for all the rivers that are included here, daily average morning water temperatures are lower than the daily average water temperature if you include the entire day. And so that variation is different, but in terms of this context, you can imagine situations where a fish caught and released in the morning may experience, quite a bit warmer water temperatures throughout the day versus a fish that, say, was caught and released later in the day, might experience some cooling into the evening and overnight. So we wanted to evaluate that in terms of, how that influences survival. And so this data, like I said, was really opportunistic and really built on, some of our observations from rivers in Newfoundland, Labrador, where we're not seeing these really strong or very predictive thermal refuges. And so this used data from that Western Arm Brook study, again, just to highlight, all the angling occurred kind of six kilometers within that counting fence location with those radio receivers. Each one of those radio receivers had a temperature logger associated with it. And the first thing that we wanted to ask to even attempt this analysis was, how consistent is water temperature throughout this watershed? So, we knew what water temperatures were at specific points within the watershed, but could we use that to, infer what the water temperatures were likely between those receiver locations? And so we restricted angling locations in the lower part of the river to 6 kilometers of the estuary, water temperature data to evaluate thermal history. And so this is what the water temperature data actually looked like. So this is the logger ID from those different stations. And then here on the x-axis, we have date. And the colors are just denoting, anywhere from 0 degrees Celsius all the way up to 20 to 28 degrees Celsius is a dark red. And it's not necessarily the water temperature I want you to see here. It's really the consistency in water temperature among all the loggers. And so basically this just implies that, water temperature throughout the entire watershed, seems to be very consistent. And so when we actually look at that difference in water temperatures across all 5 loggers, it was only 0.44 degrees Celsius. The min amongst loggers was 0.10 and the max was 1.11. And so what this means is, water temperature consistent, so we can use water temperature nearest to the salmon's position as a reasonable approximation to determine acute thermal history. And so now that we have thermal history, essentially, we can look at, what it was before and what it was after. And we also have survival probability versus water temperature from the Western Arm Brook study, which I just showed you earlier. We then made some assumptions to look at, thermal history before, during, and after that catch and release event. And so for before, given that all catch and release events occurred within 6 kilometers of the estuary, we restricted the pre-catch and release thermal history period to 12 hours, which was thought to be a reasonable approximation given that the angling occurred in designated areas. Then, of course, at the time of the catch and release event, water temperature at capture and release was used previously, and that's what generated this figure here. And then for the post catch and release thermal history, because estimates of survival were lower in the angled salmon 1 and 10 days post release, but converged at 10 and 30 days post release, and mortalities in the angled fish that did occur happened at 1 and 5 days post release, with the next subsequent mortality not occurring until 17 days post release. We restricted our analysis here to 5 days post release and used water temperature over this period or up to the time of death. And so if you look at that data, so on the y-axis here, we have the water temperature at capture. On the x-axis, we have the water temperature history. So this is, and then it's the water temperature history is split by color. So pre-capture is that 12-hour period, is those black dots, and post-capture is the 5 days gray dots here. And you can see that there's a very strong relationship between water temperature at capture and water temperature before the catch and release event and after the catch and release event. So regardless, pre, during, and post catch and release water temperatures were highly correlated. And this suggests that salmon that encountered warmer water conditions during the catch and release event also encountered warmer water conditions before and after the catch and release event. So if the river's warm, it's likely going to be warm before and warm after. If it's a cooler temperature, it's likely going to be cooler before and after. There's not going to be these huge, 10, 12, 15 degree swings in water temperature, at least in the river, Western Arm Brook. And so when we start piecing together these thermal histories of these individuals, you can see that on the y-axis here, we have water temperature. On the x-axis, we have the capture period, so the pre-thermal history, at the time of capture thermal history, and then the post-thermal history. And so we split this by alive, so we just use the angled fish for this analysis. And so the ones that survived and were angled are the gray dots and filled in here with their different thermal histories. The individuals that died are in black. So these are these individuals up here. You can see the strong effect of water temperature. And then there was one individual that died at quite a low temperature, but this individual was noted to be bleeding at the time. And so we include that here in the red, but we didn't include that actually in the analysis. And so when you restructure these thermal histories and you look at, what combinations do we have, we see that some salmon did encounter mean water temperatures that were on average 4.4 Celsius cooler and 2.9 Celsius warmer prior to the catch and release event, and 3.3 Celsius cooler and 5.5 Celsius warmer on average after the catch and release event. So there was some thermal history differences among individuals. And so, but again, regardless, cool to moderate water temperatures increase survival. And so here's some data from that. So on the y-axis here, we have the pre-capture change in water temperature. So if you're above this 0 line, you were warmer prior to the catch and release event. If you're below this, you were cooler prior to the catch and release event. And then we did a similar scenario for that post-capture change in water temperature, this 5 days post-release. And so if you're above that 0 mark, you were warmer after the catch and release event. And if you were below that 0 mark, you were cooler after that catch and release event. And so first thing that should jump out of you is you see that there's, when you look across that 0 line, you can see a lot of variation in that kind of 10 to 15 degree mark. Rivers cool and warm, based on the day, whether there's lots of sunlight, the river has a lot of capacity to warm and cool. But as you start approaching these warmer water temperatures, the river only reaches a certain, maximum. And then from there, basically the river has nothing but to go down basically from there. And so water temperature variation decreases as you approach higher water temperatures. And so of the 7 individuals that died, excluding the individual with the hooking injury, 3 were warmer before the catch and release event and cooler after the catch and release event. 3 were cooler before the catch and release event and warmer after the catch and release event. And 1 was cooler before and after the catch and release event. And so despite some salmon encountering cooler conditions post-release, 4 of 18 salmon still died when caught and released at water temperatures greater than 20 Celsius, whereas only 1 out of 13, so 8% of salmon that were caught and released at less than 20 Celsius but experienced mean water temperatures greater than 20 Celsius post-release died. Now on to the third question. So, we've looked at, the relationship between water temperature and catch and release survival in different aspects, pre, during, post, and put some numbers around that. And so what I wanted to do was really bring this full circle. And we asked the question, how can various water temperature related fishery closures affect outcomes for the salmon and angler? And so this is quite a lengthy paper that we published in 2024. If you haven't seen it, please go check it out. It goes through a whole slew of scenarios and ideas that are important in the understanding of catch and release. And it sort of allows us to start moving away from, what is the individual survival probability of a salmon following catch and release, and starts asking questions, well, what does this mean for the population? What are some of these other considerations that we need to take into account? Obviously, not all fish are caught above 20 degrees Celsius. There's a lot of angling and a lot of salmon caught, at least in Newfoundland and Labrador, kind of in that 0 to 18 degree range, or sorry, in that below 20 degree, that kind of, 15 to 18, 12 to 18 range going on during the early part of the season. And so just a little bit of an introduction. So history of water temperature related closures in Newfoundland and Labrador, it's nothing new. So water temperature related fishery closures in Newfoundland and Labrador are nothing new and go back to at least the mid 1970s. But a formal criterion for closing rivers to angling was established by DFO in 1988. So it's been around for a long time. Several changes over the years. In 1988, rivers would close when mid-afternoon water temperatures, typically the daily maximum, were greater than 22 Celsius on 2 consecutive days. Now this changed in 2018. So DFO lowered the criterion for closing rivers from greater than 22 Celsius to greater than 18, and then modified it in 2019 to allow only morning angling when water temperature is greater than 20 Celsius. And so in this case, the river is closed to angling from 10:01 each day to 1 hour before sunrise the following day. At the same time, the Newfoundland Labrador region also made changes to the number of fish that could be caught and released in a single day. So prior to 1986, there was no limit on the number of Atlantic salmon an angler could catch and release. However, a limit of 4 fish per day was imposed in 1986 and further reduced to 3 fish per day in 2018. And so these are the different contexts, the different kind of management structures that we attempted to evaluate. And so one of the first parts of this that one of the questions we wanted to ask is, is morning angling effective at limiting angling activities to cooler water temperatures? I talked a little bit about this earlier, but this used thermograph data collected from 2021 angling season for 9 DFO monitored rivers across NL. Rivers were chosen based on geographic distribution and available data. We have a lot of rivers here, but we only have a limited amount that we actually have thermograph data in. It's changed a lot since this was studied, but at the time, this is the data that we had. And then mean hourly water temperature is calculated for the morning period. This was from about 6 o'clock in the morning to 10 o'clock. This is that morning angling period. And then the daytime period from 6 o'clock in the morning to 9 o'clock at night. And so these are the rivers that we use. So combination of rivers from Newfoundland and Labrador. Again, on the y-axis, we have water temperature. X-axis, we have the fishing season date. You can see that there's a lot of variation among rivers, but again, mean day temperature is in black here, and the mean morning temperature is in gray. And so you can see that for all these rivers, morning angling, the water temperatures during the morning are quite a bit lower than you see in the day temperatures, lower for some and not so much for others. But when you do this analysis, you pull these rivers together, what we got was morning angling resulted in a 1.7 Celsius average reduction in angling water temperatures across rivers. And also the number of days in which angling water temperatures were greater than 20 Celsius was reduced by 64% from 28 days to 10 days on average across rivers over the salmon season when morning angling was implemented. So it does seem that it is effective at what it's supposed to do, and that's lower the water temperatures in which fish are angled, but it's still allowing for fishing opportunity to occur. And so let's just jump back into the main question here. So how can various water temperature related fishery closures affect outcomes for the salmon and angler? And so for this, again, it's not necessarily focused on the number, it's focused on how the numbers change when we apply these different management measures. So again, somewhat of a desktop exercise, math exercise, but it really gives you an understanding of, the importance of, when these fish are caught and released, when is predominantly those fish caught and released, at what water temperatures, etc. And also, how different management strategies will affect, things like angling opportunity. And so we combined water temperature records, daily salmon returns, and broad catch data averaged over the 2016 to 2020 seasons from DFO science records from the Newfoundland Atlantic Salmon Abundance Monitoring Program with the catch and release mortality for given water temperature model from the Keefe study. So that's the one that I presented from Western Arm Brook. To estimate the total number of salmon caught and released per day across the 2016-2020 angling seasons, the mean reported proportion of the caught and released Atlantic salmon per day was multiplied by the estimated mean total number of fish caught and released from the entire season. The protocols evaluated include no closure, full closure at 18 Celsius across 2 days, full closure at greater than 20 C across 2 days, morning angling only at greater than 18 Celsius across 2 days, and morning angling only at greater than 20 Celsius across 2 days. So in addition to each protocol, the number of fish caught and released per day under more restrictive catch and release limits, 1 or 2 fish per day, at the moment it's 3 fish per day, was also determined. This was done by reducing the number of caught and released fish from 3 to 2 or 1 fish, depending on the protocol being evaluated. And so for days in which an angler recorded their daily maximum of 3 caught and released fish, we then lowered that day to if the maximum was 2 or if the maximum was 1. And so again, this is just a visual of how that desktop exercise looks. And so here in panel A, we have water temperature and fishing season date. Again, the black line is the mean day temperature, and the gray bar is the mean morning temperature. So this is, just showing the thermal profile that was used for this evaluation. And again, we have horizontal lines just showing 18 and 20 degrees Celsius. So you can see that the river, there were periods that it was above, 18 for sure, and above 20 as well. Here's just in panel B is just showing salmon returns. So because this is a monitored river, we're able to actually start translating this into the percentage of the population that this mortality, to estimate the amount of mortality versus the entire population. And so you can see on the y-axis here salmon returns, x-axis fishing season date, and you can see that fish start entering kind of that mid-June period when the season opens to a peak kind of in and around July, and then starts sort of teetering off in August and September. And so, what's important is, when you're evaluating this for a given river is, when are these fish returning? And so, obviously having warm water temperatures in July when a lot of fishing's taking place, there's a lot of fish in the river, we'll have different outcomes for the salmon than, if they come into the river kind of later in the season, August, and there's not much fishing taking place. From there, again, on the y-axis, number of fish caught and released per day. On the y-axis, we have fishing season date, and you can see, as fish start entering the river, they are being caught and released. And then these lines here, those different protocols. So this is really that desktop exercise on what's included in that evaluation for the various protocol. And so something like an 18C no angling protocol, you can see the water temperatures start creeping up here. There's some fish being caught and released. And then basically you wouldn't include this period here because the water temperature is above 18. So technically that river would have been closed at that period. And so you do that for the different scenarios, and you can start putting numbers around catch and release mortality and using those and implementing those various protocols. And then, so when we take the number of fish caught and released, we know the water temperature, we can then apply that catch and release mortality model at a given temperature. And again, we can calculate, how many fish may have died during that catch and release event over that period. And so this is what those numbers look like. So how do various restrictions, water temperature thresholds influence outcomes for the salmon and angler? And so here's those daily release restrictions, 3, 2, and 1 fish per day. This period, these groups here under no temperature restriction. These individuals here are under temperature restriction, but a full river closure. So closing the river completely if water temperatures are greater than 18C after 2 days. This is a full river closure if river water temperatures are greater than 20C after 2 days. This is a temperature restriction with morning fishing only. So again, 18 degrees across 2 days, but allowing for morning angling. Water temperatures above 20 degrees, but again, allowing for morning angling. And so one of the things to take away here is when you start looking at the estimated catch and release mortalities, in brackets, that's the percentage of the population. And so you can look at pure numbers, and then you can look at the percentage of the population. And so the first thing that I just want to highlight here in green is that catch and release mortality relative to total salmon abundance was low for all angling protocols evaluated and ranged from 0.4% to 2.6%. Now again, that's under this temperature regime for this river and its characteristics. And so you can see that here that, under no temperature restriction, our estimated number of fish mortality as a result of catch and release, 474 individuals if he allowed a 3 fish retention. And then the lowest is with a 18 degrees Celsius full river closure and only 1 fish retention. No surprise there, reduce the number of fish that are allowed to be caught and released. And you reduce the temperature in which those fish are caught and released, you're going to get less mortalities. Now, one thing, and then down here is the estimated, so this is basically your angling opportunity. So it's the estimated daylight hours of fishing opportunity per angler. And so obviously with more restrictive measures comes a trade-off with fishing opportunity. And so what you see is with complete river closures due to warm water temperature protocols resulted in less catch and release mortality than no water temperature restrictions or partial closures. No real surprise there. However, the 18C and 20C morning angling only protocol resulted in a 50% and 16% increase in angling opportunity when compared to 18 degrees Celsius and 23 degrees Celsius full river closure protocols, respectively. And so just to illustrate that, you can see the dramatic increase with a relatively, again, it's all about a balance between angling opportunity and balancing catch and release mortality at various water temperatures. But again, it's not for me to decide, but you can see that, you're with allowing morning fishing only, at whether it's 18 or 20 degrees, you do allow for quite a bit more angling opportunity to occur, with only somewhat of a modest increase in that catch and release mortality. And so a lot of this is driven by, when those fish are caught and released and at what water temperatures. But you can see that with no river closures, the average water temperature over the season was in and around 19.8 degrees Celsius. But then when you start putting these restrictive measures of 18 degrees and a full river closure, it limits that angling water temperature to 15.8. If it's 20 degrees, it's 18.6. But if you allow for morning angling only, again, it lowers the water temperature as well to 19-degree average over the season. And so, it's really about this balance between, allowing for a fishery to occur, but also minimizing mortality. And there's a lot of factors that drive that. And we talk a lot about that in the paper that I mentioned earlier. And so with that, I just want to thank the foundation for setting me up with this webinar, and also to the numerous co-authors and various meetings that we've had that's really contributed to this work.
Great, thank you so much, Travis. That was an excellent presentation. So we do have time for questions. If you have a question, please raise the little hand icon on your screen, and I'll be able to unmute you so that you can ask the question. This would be the preference, but if this function is not working for you, you can also use the chat or questions box, and I'll read your question out loud. So okay, we do have a couple questions. Let's see. Okay, so first up we have Bill Haley. Go ahead, Bill. You just have to unmute yourself there. Oh, you there, Bill? Okay, not sure if he's there. So we'll move on to Brent Locke. You can go ahead and ask your question, Brent. Can you unmute there, Brent?
I'll have a go if it's free.
Hi, Alex.
Hey there.
Go ahead.
Well, thank you very much. That was a very impressive suite of studies. I think that you've done a lot to advance the cause. Also interested in your work on adaptive life history strategies, because that's where my doctorate was in '84. So you talk about long time periods. Mine's a bit longer than yours. So I'm going to ask a couple of questions with a bit of hindsight here. In 1996, I wrote a FCAS-FCSA document that looked at water temperatures. And in it, I talked about needing a formal policy for river closure and subsequent reopening. I'm really glad that 20 years, 30 years on, we've actually got there. First of all, as I recall, work that I was involved in, one of the students who published, Booth, had established that grilse appeared to experience more severe physiological disturbance in catch and release than MSW fish. And I think the Western Arm Brook is primarily a grilse river, is it not? As are most of the rivers in Newfoundland, not Labrador. So you have a couple of other rivers thrown in, but it's predominantly being driven by Newfoundland and Labrador. So that's the first comment, and I think that I'd like you to address that, as well as the next question, which is understanding the importance of a precautionary approach. The difference between 18 and 20, particularly when you've shown in your last synthetic study that you're losing very few fish anyway. And a morning only angling situation, you're gutting the angling fishery, in essence, particularly in places somewhat akin to Newfoundland. I'm thinking predominantly in New Brunswick, where outfitters rule, and outfitters aren't going to attract people coming for fishing between 6 a.m. and 10 o'clock in the morning or whatever it is. So given that fairly small mortality difference between 18 and 20, I think that one would increase the angling opportunities very significantly, whilst not affecting stocks very much. In some cases, yes, you're going to need to shut the fishery down probably totally, and anglers will buy into that. But might 20 degrees not be a better limit to ensure that they're angling and economic opportunities?
Yeah, so yeah, it's great that you're on the call. I am familiar with your work as well. So yeah, it's great to have you on the call. There's definitely been people working on this for a long time. So to your first question, yes, 100%. So, a lot of this, and I kind of missed the opportunity to say that, but up front, I was going to make a bit of a disclaimer. So that recent paper that we published, Considerations for Water Temperature Related Closures, life history of salmon is one thing that we definitely include in there. So there is some evidence to suggest that one-sea winter fish, particularly ones that are early run or into the river, soon after entering the river, maybe more susceptible to catch and release mortality than a bigger multi-sea winter fish or fish that have been in the river for a longer period of time. There does seem to be some evidence around that for sure.
And kelp in particular.
Kelp in particular, yeah, exactly. But I would say with kelp, it's hard to disentangle kind of the water temperature effect, especially when there's a kelp fishery going on, in terms of, all kelp will be captured at relatively cooler water temperatures. So it's hard to tease out, that kind of effect of water temperature when, those fish won't be there when there's, at 20 degrees, right? So whether is, the data suggests, or the study suggests, that kelp definitely are, survival of kelp following catch and release is high. But whether that's because they're all captured at cooler water temperatures where these studies were done, versus having a kelp at 20 degrees, like it's tough to to make that argument because it's just not going to happen, right? So, but there is some evidence definitely one-sea winter fish, are more susceptible, and so this is one of the situations that we're in, right, where my work is the relationships and the sort of generalities of our findings. Can be applied broadly, in terms of, what they mean, the relationship between water temperature and survival. But, what we do caution is that, what's good for Newfoundland, Labrador, might not be good for, the Maritimes, or, where you have more multi-sea winter fish, or you have fish entering rivers later in the season, in August. If you got a big fishery in August, September, when you're more likely to encounter those really warm temperatures, maybe those protocols need to be a little bit different. But, one of the things that matters here is that under our conditions, fly fishing only, etc. These are the mortality assessments, primarily grills fisheries, and this is what we see. And so, the other part of it is in terms of the water temperature closures. I'm not in a position. Our science is really just to put the numbers on there. I will say that whether it's 18, 19 to 20 degrees, where that where that really starts ramping up. Again, there's not a ton of studies. There's not a lot of data, outside of, say, the Western Arm Brook study, in those 23, 24, 25 degree range water temperatures. So we're really fitting a model to that and assuming that, it's going to follow that trajectory. Now, whether that trajectory is as steep as the model predicts or not, that's sort of debated. But, the survival is not going to, the mortality, survival is not suddenly going to, increase or something beyond those water temperatures. But again, it's a combination of, it's hard to find a study, again, these warm water temperature periods in that kind of, 21, 22, 23, 24 degree range, the length of time to go in, catch and release fish, have a control group is quite narrow. These studies are hard to get off the ground in the first place. So that's one issue. The other issue is catchability of those fish at those water temperatures. They tend to be slightly lower. So being able to get enough fish, representative sample size, and also, we know the mortality will be high. So, are we willing to, lose 50% of our sample size at, 21 degrees to show that, the survival is, 2 degree difference or something, right? Like it becomes a bit of a balance between what we can do, what we, what people want to do, and what's acceptable. So that would sort of be my answer to that, I guess.
Thank you.
Okay, great. We have a question from Bill Haley. So I'm going to try to unmute you now, Bill. Still doesn't seem to be working. I do have his question though in the chat. So Bill's question was, are you concerned that such small salmon were used for the Western Arm study? The average size in the Margaree more than 12 pounds, but DFO may apply the findings to our river, he says.
Yeah, so again, our examples are from Newfoundland. I work in Newfoundland, that is our examples. And, they're like I said before, I sort of answered this question already, is that, different regions, different conditions, when fish are in, definitely one sea winter that makes up, most of the rivers on the island. If you get a chance, read that paper. We do talk about, just applying these things broadly without these other considerations. There's more to this than just, life history of the salmon. There's the animal, there's the human dimension part of it. There's, when are fish being caught and released? How do fish, how do anglers, what times do they go out? So, that's basically where I'll leave it. I would be cautious to apply these things broadly. The relationships are there, but, again, yeah, maybe multi-sea winter fish are, maybe their survival is a couple degrees, a couple percentages higher than, say, grills. But, are we willing to go out and do those studies? If people want to do those studies at those really high temperatures, you need to be willing to lose those fish. And, and is really the outcome of that, to be able to say, mortality is 2% higher than it was in grills, I don't know. And that's really for others to decide, I guess.
Thanks, Travis. Okay, we will try to squeeze in one more question. So we have a question from Robert Chiasson. Bob, if you can go ahead and unmute yourself, then you can ask your question.
Hi, good afternoon. Thanks
Hi.
for the webinar. Very interesting. The question I have, I guess everyone understands that the higher the temperature, especially around 20 degrees, the more mortality there is. But the question I have is that the higher the temperature, the success rate of anglers is also reduced. So the total numbers of fish that are affected are a higher percentage of a reduced number. Did your study take that into consideration, and is there a way that we can capture that?
Yeah, so I didn't include it in the webinar, just given the time, but catchability and water temperature is something that we looked at 2 ways as well. So we actually looked at it in the Western Arm Brook data study. And we also looked at it with a unique situation in a river called Northwest River. And so that river is a little bit different. It operates within the park. And so anglers, they need a provincial license, but then also a park license. And so it's predominantly a retention, it's a retention fishery only. And those individuals that are leaving the park have a park tag, so we know how many fish are caught on a given day at a given water temperature. And so basically what it allows us to do is it's also a monitored river. So we know how many fish are coming into the system, the water temperature on a day. And again, these openings of this river are relatively short. They might open, once conservation limits are achieved, it'll open the river for, a week or 2 weeks or something. And then it's basically a big free-for-all for anglers over a set of pools on this river. And again, a retention fishery only, but we can apply that data to understand catchability. We have the inputs. We know how many fish are likely in that river or in that sort of area at any one time. We know how many individuals bought a license to go fish that. And it's a bit of an estimate because, if you buy a license, you're not necessarily going to go there, but then why would you go to the park, buy a license, and then not go fishing? So it's a reasonable approximation, at least what we think. We know how many fish are caught on a given day, and we know the water temperature. And so we actually have a paper published. It's called Catchability of Atlantic Salmon at Water Temperatures. And so what we found was, like you say, so definitely a decrease in catchability of fish with increasing water temperature, but that relationship wasn't as strong as often talked about. So there definitely was a decrease there, but there was still, again, there's a lot of anglers over a relatively short time frame. There was a lot of fish still caught in those 22, 23, 24 degree range temperatures. So it's not a scenario where the added mortality at those higher water temperatures really balances out the reduced catchability of Atlantic salmon.
Okay, thanks. Thank you.
Okay, great. So I guess we'll have to cut off the questions there since we're going over 3 o'clock now. Thanks again, Travis. If you do have a question for Travis, you can reach out to the foundation and we'll pass your question along. And we have recorded the session and it will be available on our YouTube page later this afternoon. I would like to remind everyone that our next webinar will be held on February 19th with Dr. Craig Purchase from Memorial University. And the title of the webinar will be Reproductive Quality of Virgin versus Repeat Spawning Atlantic Salmon and How Different Diets May Lead to Altered Hybridization Threats from Invasive Brown Trout. So again, a big thank you to Travis and to everyone who participated. We will hopefully see you in the next webinar. Bye now.
Thank you.